So I would like to talk about the processing of lignocellulosic materials into fiber in a twin screw extruder, the physical properties of the produced fibers under the aspect of the application as a growing substrate. So first of all, I would like to show you where the wood chips we process come from and how they are processed. So the harvest of the wood chips from short rotation coppice is usually done by mower chipper or modified forage harvester. Landscape management residues are harvested manually and chipped by a manual chipper, and then there's the wood chips. There's shipped to the storage.
Christian, sorry, Christian, don't forget to change your slides.
I did. How is that not happening? You see at the first slide?
Do you still see the first slide?
No, now it's 2. I see 2.
Okay, now it's fine.
Okay. So maybe the internet connection isn't the best. Sorry.
No, we can see it now. It's fine.
Yeah. Then the wood chips are stored at dried at the storage locations. That can be done technically or just putting up big piles, and due to this microbiological activity, they heat up themselves up to 60 degrees and dry by themselves. The wood chips are then extruded and dried for storage reasons. My next slide shows you how a twin screw extruder looks like on the inside. So on the pictures there, you can see what our extruder at ATB looks like. The defibration of the wood chips takes place by the pressure, shear, and squeeze comminution, the relaxation comminution due to the steam explosions, because we have temperatures up to 120 degrees Celsius inside the extruder in the process. The wood is swelling. This also causes defibration, and there's also partial release of wood ingredients like extracts, like lignin. The fiber that is produced and the properties of that fiber is majorly affected by the aperture setting. The aperture is the part where the red arrow points at. So that basically means a smaller aperture leads to smaller fiber, and a large aperture to more coarse fiber. The water content also affects the material, the fiber, the water content of the raw material. A high water content causes coarser fiber, and low water content causes smaller fiber. On this slide, you can see now what the raw material looked like before we processed it and after processing. So there was olive pruning from Turkey, which was sent as chips to ATB. We extruded it and got this fiber you can see on the right side. And we have 32 hectares of poplar short rotation coppice at ATB, where we have a lot of poplar every year for our heating system. But we also use some of it to produce fiber, as you can see here on the lower picture. What are the requirements on the of the fiber quality? So we want to have a high water holding capacity and a high air volume, even at full water saturation. And it needs to be stable, yet has a high porosity. So this is all important for growing, for fiber as a growing media. It also needs to be chemically inert and free of microbiological contamination, so we don't have mold inside our growing pots. We focused on black locust, poplar, sea buckthorn, hop, grapevine, and forest biomass because there's a high availability of these raw materials at ATB. We would also have had a closer look on other materials, but we only got 100 kilograms of, for instance, olive and thyme and sage and all the materials from Turkey. But since we do statistical analysis on those materials, and we need a lot to get data, we could only use black locust, poplar, sea buckthorn, and so on for our investigations. With the standard 13041 soil improvers in growing media, we tested various physical properties, for instance, high water holding capacity, air volume, and other physical properties as well. On my next slide, you can see how we designed the water tension measuring box. So you have the 3 double ring cylinders sitting on the sand bed here. Then we have a flexible hose which is attached to a water container, and this whole container can be set at a specific height. So the water column inside this flexible hose basically sucks the water out of the sand bed, and this drains the fiber we are testing, and then you can determine how high the water holding capacity is. We also did Sieve analysis, as I already said a couple of times. This took a lot of time to do. Here you can see our different Sieve Apertures. We set the fine fraction to 0.5 millimeters and the coarse fraction to 3.15 millimeters. And as a result, we got this this image where you can see the 6 different raw materials extruded at 20 millimeters. The 6 raw materials I was talking before, the ones that are highly available. It is clear to see that poplar and forest biomass have quite a lot of fines within the fiber extruded at 20 millimeters, and hop or grapevine and black locust, they are certainly coarser than the other material. We also show the X50 value here in this image, which basically indicates the median of the particle size for each material. Okay. I want to show you also this slide where you can see the water holding capacity as a function of raw material, all extruded at 20 millimeter aperture setting. So all the six different raw materials were extruded here and then tested for water holding capacity. The first column here is white peat, which is our comparison value basically, but the white peat, of course, wasn't extruded. We bought it at a hardware store and tested it for water holding capacity the same way we tested all the other. You can see here that the best water holding capacity has the forest biomass we got from Spain, and at 10 centimeter water column. Oh yeah, sorry, I forgot to mention that we tested the water holding capacity for negative 10 centimeter water column and negative 50 centimeter water column. And at the negative 10 water column, the forest biomass was the best, the second best, of course. White peat was always the best. And the hop and black locust were the best at 50 centimeter water column. Because forest biomass was very good compared to the other material, we took a deeper look into that. And here you can see that with the extruder getting bigger, basically meaning that there's less grinding of the raw material, we got a higher water holding capacity at a higher aperture, which is the complete opposite to the poplar, for instance, where we could see that we had the highest water holding capacity at 20 millimeters aperture setting of the extruder, and then the water holding capacity got worse with larger aperture settings, as well as for a smaller aperture setting. So the optimum for the raw material poplar is at 20 millimeter aperture setting. On this slide, you can see the energy consumption during extrusion at a 20 millimeter aperture. So the poplar had the highest specific energy demand, and the sea buckthorn and grapevine, they had the lowest energy demand, specific energy demand. Interesting here is that even though the black locust is a really, really hard wood and hard material, it was still better to process it in the extruder than the poplar. In this table, I put some values together, so you can see the fine fraction here, the X50 value, the coarse fraction, the water holding capacity, and the specific energy demand. The water holding capacity here, just for the 10 centimeter water column, so you can get an idea of how all the values correlate to each other. We are doing a statistic analysis right now. It's not finished yet, but there's of course going to be a correlation between the aperture setting and the specific energy demand. But we're also looking into correlation in between water holding capacity and specific energy demand, but I can't say anything about that right at the moment, right now. Okay, my last slide are the conclusions. So we did have to do a high number of tentative tests, and getting a fiber with a specific quality is difficult. And the different extruder settings affect the physical properties like water holding capacity, particle size distribution, etc., etc. We also did a lot of other tests I couldn't fit into this presentation here. So we had so many different aperture settings and a lot of different ash analysis, and we did the air porosity and all that kind of stuff. But in our paper, which we are writing right now, the first peer-reviewed paper, we will fit in as much data as we can. A very high influence on the raw material, on the fiber also is the raw material and the raw material water content. And there was also no fiber we produced that reached the water holding capacity of peat. It was always smaller. But the distance between the water holding capacity values from the 10 centimeter and the 50 centimeter water column was always smaller than the distance between the water holding capacity of peat. So the difference in between the 50 centimeter and 10 centimeter water column was always smaller. We did send some fiber to IRTA, to Spain, for growing tests. And as I said, the statistical analysis are in progress. I thank you for your attention, and if there are questions, I'm happy to answer them.